Hey everyone! Today we will be solving the 2020 AMC 12A Problem 25, and I will be showing you why the law of sines is helpful here. First, a brief introduction. My name is Benjamin Liu, or Ben for short. I have the disease spinal muscular atrophy weak type 2. This disease causes full body weakness, and I must rely entirely on my family members to perform basic tasks of living, such as going to the bathroom. However, my brain is not affected, and I have a passion for mathematics. Without further ado, let's get started. Okay, here's the problem, and I'm going to dive straight into the solution. So this is your opportunity to hit pause and ponder the question for a while. Okay, I'm going to assume you have done that. So let's get started. Okay, so firstly, the fractional part of x is a mouthful, so I'm just going to say the frac of x, or frac of x, usually. Okay, now let's get annoying edge cases out of the way. Okay, so I claim that other than the solution x equals 0, which is trivial, that x is at least 1. Okay, so let's assume to the contrary that x is not 0 and x is also less than 1. So then, since x is not 0, ax squared is positive, and the floor of x, since x is less than 1, is 0 or less. And the frac of x is always non-negative. So you have a non-positive times a non-negative, and that is non-positive. So the left-hand side would be non-positive, and the right-hand side would be positive. And that's a contradiction. Therefore, x is greater than or equal to 1, except for the solution x equals 0. So for most of the rest of the solution, let's now assume that x is greater than or equal to 1. Okay, now let's get into more interesting stuff. We're given these two pieces of information, and we want to find the correct constant a, such that the sum of the solutions of x is 420. So we have two things added here, and we have two things multiplied here. So why don't we square the first equation? So then we'll get a 2 times floor of x frac of x term. So let's do that. You square this equation, and you get this. Now you substitute the 2 floor of x frac of x for 2ax squared. So you get x squared equals frac of x squared plus 2ax squared plus floor of x squared. Now subtract 2ax squared from both sides and divide both sides by x squared, and you get this. Okay, now there's too many square roots running around, so let's, there's too many squares running around, so let's take the square root. And then we get this. Okay, now this should get you excited because this is the Pythagorean theorem. So how do we take advantage of that? Well, this is one way. Define the points A, B, C, and D as shown here. A equals x comma 0, B equals floor of x frac of x, C equals 0, 0, and D equals floor of x 0. Okay, so what do we notice? Well, we notice that B and D have the same x coordinate, and A and C have the same y coordinate. Therefore, BD is perpendicular to AC. Well, what else do we notice? Well, BD is equal to frac of x, and AD is equal to x minus the floor of x, which is also the frac of x. So ABD is an isosceles right triangle, hence the two 45-degree angles. Okay, well, CD is the floor of x, and BD is frac of x, so therefore BC is, by the Pythagorean theorem, the numerator. And AC is x, which is the denominator. Okay, so this is when we get to apply the law of sines. So applying the law of sines gets us that BC over sine of BAC, BC over sine of BAC equals AC over sine of ABC, AC over the sine of ABC. Okay, now we can rearrange this equation here so that it becomes this equation here. Divide by AC multiplied by sine BAC. Okay, but what is BC over AC? Well, we saw earlier that BC over AC is equal to the square root of 1 minus 2a. So that's where this comes from. Okay, well, what is the sine of BAC? Well, angle BAC is 45 degrees. So therefore, the sine of BAC is 1 over square root 2. Okay, all of that to say, we can find the sine of ABC in terms of A. In particular, whatever solution x we chose, when we find the sine of ABC, that value, the sine of ABC, will always be constant because it only depends on A. It does not depend on the solution x we chose. Okay, now let's go back and prove that ABC is obtuse. So notice that BD is the frac of x, remember, and CD is the floor of x. Okay, but the floor of a number greater than or equal to 1 is greater than or equal to 1. And the fractional part of any number is less than 1. Therefore, CD is greater than BD, which means that angle CBD is greater than 45 degrees, which means that angle ABC is greater than 90 degrees. Okay, so, but what do we know about the sine function on the interval 90 degrees to 180 degrees? Well, it's strictly decreasing. In particular, the sine function is 1-to-1 on the interval 90 to 180 degrees, which means that since we know the sine of ABC, we can find angle ABC itself. This means that the angle ABC is constant no matter what solution x we chose, because it will only depend on the value of A. Okay, now that we know that angle ABC is constant over all solutions x, we can subtract off 45 degrees from it to find that angle DBC is also constant over all solutions x. Now take the cotangent of angle DBC and you will get that BD over DC is constant over all solutions x. Okay, but what is BD again? Well, BD is frac of x. And what is CD again? Well, CD is the floor of x. Therefore, the frac of x over floor of x is always going to be constant. Let's call that constant D. So here we have what I just said, basically. So now let's multiply both sides by the floor of x. So we have the frac of x equals D times the floor of x. Okay, let's add the floor of x to both sides. So we factor out the floor of x and we get frac of x plus floor of x equals 1 plus d times the floor of x. Well, the left-hand side is actually equal to x. So we have that x is equal to 1 plus d times floor of x. So let's start trying some values. Maybe the floor of x is 1. Well, then x is 1 plus d. Maybe the floor of x is 2. Then x is 2 plus 2d. And this can continue, and you might ask yourself, when do the solutions stop? Well, at some point, if we make the frac of x large enough, then when we make the floor of x large enough, then d times the floor of x will exceed 1, and the fractional part of x is always less than 1. So at some point these solutions do stop. Okay, to summarize that, we have solutions 0 all the way to xk, and 0 is added back for completeness. And for any integer I between 1 and k, we have that xi equals I times 1 plus d. And remember what this I was. This I was the floor of xi. So therefore, we have this. Okay, let's sum this equation from I equals 1 to I equals k. Then this becomes 1 plus 2 plus 3 all the way to k. This becomes x1 plus x2 all the way to xk. And this becomes 2 plus 3 plus 4 all the way to k plus 1. Now we can add 1 to this to make it nicer. And we're given that the sum of the solutions is 420. So we have that by the sum of an arithmetic sequence formula. This becomes this, and then we have the 420, and then we have this, which is equal to this. So now we can solve this equation for k. It's pretty easy. K is an integer, has to be. So k equals 28. Okay, now we have that 420 is the sum of the solutions. What was x1 again? Well, x1 was 1 times 1 plus d. So that's where this comes from. And then x2 is 2 times 1 plus d, and so on all the way up to 28 times 1 plus d. Now we can factor out the 1 plus d. So it becomes 1 plus 2 plus 3 all the way to 28 times 1 plus d, and that's equal to this. Okay, now we can solve for d. When we do so, we get d equals 1 over 29. Okay, so now we have a solution. We have a solution x. We can use x1. In particular, x1 is 1 plus d. So let's plug in 1 plus 1 over 29 for x, and you get this. Okay, square both sides and simplify a bit, you get this. So a equals 29 over 900. Okay, now what did the question ask again? Well, we wanted p plus q. So that is 900 plus 29, which is c. And we are done.